Hello everyone, welcome to the Material Science class MIC 300. This is chapter 5. In this chapter we are going to discuss the diffusion. So before we go through why the study of diffusion is important, let us define what is a diffusion or know what is a diffusion. Diffusion simply is the process of the transfer of mass from one position to another position, from one part of a system or environment or a material to another part within the same system or the same environment, or even the transfer or the transport of mass from one environment or material or system to another totally different material, system or environment. So the transport of the mass from one position to another position, whatever it is, this mass, it is known as diffusion. So diffusion in general, it is the process of transfer of mass from one part to another part, one position to another position. But since we are talking here about material science, so the mass that is going to transfer, definitely it will be atoms. So the atoms, why atom? Because as we defined in chapter 2, we said that the atom, this is the smallest bit of the material. This is the smallest building unit of the material. The smallest thing inside the material is the atom, which we agreed to represent this atom like a point, but this point has a specific mass. So if you have an atom that is going to transfer or transport from one position to another position, this is known as diffusion. Like you do have the atom at a certain lattice site, as we defined what is a lattice site. This is the position, this is the location of one atom inside the atomic structure of the material or the crystal structure of the material. So for some reason, if this atom is going to leave its position and is going to attain another position, this is known as diffusion. This kind of process is known simply as diffusion. So diffusion is the migration, is the transportation or the transfer of the atom from one position to another position. This is known as diffusion. So diffusion, it is the process of the transfer of atoms, the transfer of mass, like atoms, for example, either within a specific material, within the same material, or from one material to another material. So this is generally is a diffusion. Diffusion also can be thought as the migration of atoms from one substance, from one part, from one material, substance, from a region of a high concentration to another region of low concentration of this substance. Like you do have the atom of one substance, like you do have a material. Within the same material, even if the atom, as I said, is going to transport, is going to migrate from one position to another position, and basically what is happening that it migrates from the high concentration to a low concentration region. What does it mean? It is very similar to this schematic or representation. Assume, for example, because one of the things or the benefits of diffusion that we could use diffusion for making alloys. And we said that the alloy, it is like a metal with non-metallic material with different concentrations both to form an alloy. So for example, if we're going to talk about the copper nickel alloy, so the copper, this is one material substance, this is one material, the nickel is another material. Nickel, this side you can see that this is the nickel rich side of the material. Like it means that all this side, there is 100% nickel, there is 0% of the copper atoms here. As already shown here, all of these atoms that located over this side, all of them are nickel atoms. By this red atom represent the copper atoms. So we do have here 100% of nickel and 100% of copper, but we do have 0% of copper here, 0% of nickel here. So we're gonna say that this side, if we're just gonna consider the nickel atom, this side, it is high concentration side with respect to the nickel, and this side is low concentration side with respect to the nickel. We're still talking about the nickel atom itself. So if we excite this material to do diffusion, and this requires certain things to do this diffusion, it means that we have to give a certain amount of energy, and enough amount of energy to this atom to diffuse, to transport from the nickel side, which is with high concentration, to the low concentration side of the nickel. So to enforce any one of these atoms to diffuse, to migrate from this side to this side, this requires a certain amount of energy, and this process is known as diffusion. The same thing is going to happen. This requires in the meanwhile that the carbon atoms, the carbon atoms also to migrate from its high concentration to the low concentration to the other side. So it is kind of exchange. Like this nickel atom is going to leave its side empty for a carbon atom that is going to attain this, or is going to take this lattice side. So it is like a change of the lattice sides between these two different atoms from two different materials to form an alloy. So we're going to end up with an alloy, like we are mixing these atoms together. So the transportation or the transport or the transfer of one atom to another, from one lattice side to another lattice side, is known as diffusion. Alright, so like for example, if we consider this figure for further demonstration about this point, as shown here, the nuclear is 100% over this side, and it is kind of decreasing, the concentration is decreasing to be 0 over the other side. Before diffusion, this is after diffusion. Before diffusion, that this side it was completely 100%, and directly you're gonna have 0% over the other side. The same thing for the copper. But once these atoms they gonna start, the copper and the nickel atom, they gonna exchange sides. This is gonna end up with an alloy within this middle region. This is like a mixture of both nickel and copper, but this side there is 100% copper, this side is 100% nickel. So we're gonna end up with an alloy in the middle here, right? This is one of the methods of making alloys. So anyway, you're gonna have one high 100%, very high concentration, and the concentration is going to decay or decrease to be 0 over the other side. The same thing for the copper. We start with 100 concentration, and it's going to decrease to 0% concentration over the other side. And in between, we're gonna end up with an alloy. It means that this is over this diagram of the concentration distribution or over the position. This is gonna give you, like in the middle here, we're gonna end up with an alloy, but here we're gonna end up with 100% nickel, 100% copper. Make sense? How we can achieve this diffusion? This mainly require energy, that we should give energy, and we are going to explain this with more detail, for this atom to diffuse, for these atoms to transfer, to migrate from one location to another location. And the easiest way to do so is using heat, is using temperature. By increasing the temperature of the material sample, this enhances more the possibility, or increases the possibility of the diffusion of these atoms. Make sense? So generally speaking, what is a diffusion? It is the transfer of atoms from one lattice side to another lattice side, whatever within the same material type, or diffusion between two different materials to form an alloy, like the case of copper nickel alloy. Diffusion also, it can be thought as the migration of atoms from one substance from one region of a high concentration to the another region of low concentration. Also, diffusion, it could be either interdiffusion or self-diffusion. So what is the difference between interdiffusion or self-diffusion? So let us start with the self-diffusion, because it can be easily understood from the definition. From definition, self-diffusion indicates that it is kind of the same within a diffusion that takes place inside, within the same material type. There is no two different materials, there is just one material type. So it takes place for pure metals, pure metal. There is no any other non-metal material, where all atoms of the same material type, we're still talking about self-diffusion, same material type, exchange position. And this is happening in case that we are heating the material. As we are increasing the material, we are enhancing the diffusion. We are enhancing the exchange in the lattice side between these different atoms. Like for example, this is the material at a certain temperature, and this is after we are heating the material, after we are increasing the material. And in this case, for example, we didn't change the crystal structure. We still have the same arrangement of atoms. If we just removed these letters, we weren't gonna feel with any change in the lattice side or any diffusion. But physically, there is a diffusion that is happening here, that these atoms, they are exchanging position because of the heat. So the diffusion mechanism, it takes place within this material, within the same material type, but it will not be clearly seen as long as there is no change in the crystal structure. But this doesn't mean that there is no diffusion. No, the diffusion is there and is happening. And this is very clear if we give marks or names to this atom, like this atom A, it changed its position to another lattice side. The same thing, C, it became there, D, it became there, B, it became there. But we're still maintaining the same crystal structure within this diffusion process. There are some other diffusion processes that would involve change in the crystal structure, and this is going to take place when we are heating the material to a temperature higher than the recrystallization temperature of the material. This recrystallization temperature is like a material property, and we are going to discuss this with more detail over the next chapters. But at this high temperature, the diffusion would end up with kind of change in the crystal structure of the material before heating. After heating, we're going to end up with two different crystal structures. But in many of the cases, during the diffusion process, we are trying to maintain or keep the crystal structure as it is. No changes over the crystal structure, but it changes over the lattice sites. This, as I mentioned, when we're going to look to the material after heating or before heating, we're going to end up with the same material structure, atomic structure. We won't going to feel with any diffusion, but this doesn't mean, as I mentioned, that there is no diffusion. No, a diffusion is there, already happened, but by changing the lattice side of these atoms. So this is what does it mean as self-diffusion. Again, it occurs or takes place within the same material type. But interdiffusion or impurity diffusion, this indicates that definitely there should be two different materials. And this is one of the essential or practical use of diffusion mechanism for making alloys. As we mentioned, like the case of nickel and copper, these are two different materials. So one of them will be with a lower concentration than the other material type. And that's why it will be counted, the one with lower concentration, it will be considered like impurity, as we discussed in chapter 4. So in this process where atoms of one material or metal diffuse into another metal or another material, whatever, or both are metallic materials or both are metal and non-metal, it depends. But this is what does it mean, a diffusion. So interdiffusion, it means that, which is also known as impurity diffusion, it is the process of atoms migration between two different materials or two different substances to form an alloy. For example, like the case of nickel copper alloy. Make sense? Alright, so given this definition of the diffusion, so why the study of diffusion is important? We skipped this slide, right? We had to define to you what does it mean diffusion first, so you could understand the importance of this diffusion thing. Simply, we said diffusion is the migration of atom from one lattice side to another lattice side. And keep in mind that this requires something, like we have to excite this material to do so. And this requires that we should give enough energy to this material to move, to migrate from one lattice side to the other lattice side. One of the easiest ways to do so is heating the material. Heating or increasing the temperature of the material. This would enhance the material or increase the possibility of the atom diffusion inside the material. So materials of all types are often heat treated to improve their properties. Heat treatment, and this is what will be covered over the next chapters, is that this is one of the approaches of enhancing or changing some of the properties of the material, especially mechanical properties. Like this, in this process, it involves that we are heating the material to a certain temperature level. Then we are cooling down this material at a certain rate. So we're going to end up with the changes into the material properties. This thing will be covered with more detail, as I mentioned, over the next chapters. But since we are going to heat the material, so we should expect that there is a diffusion that is going to take place here. We said that diffusion requires energy to excite this atom to migrate from one lattice side to another lattice side, and this can be simply done by heating. So since heat treatment, it is one of the essential processes of changing the properties of the material, it means that during a heat treatment process, always it involves atomic diffusion. It means that definitely there is atomic diffusion that is going to take place. So we have to consider this. So that's why this is one of the reasons why we should study or understand the atom migration from one lattice side to another lattice side, which is known as diffusion. Often an enhancement of diffusion rate is desired in some application, in some situation. We would like to increase the possibility or enhance the diffusion rate, enhance the possibility of the migration of atoms from one lattice site to another lattice site. In some other occasions, however, we should reduce the diffusion. We should work on reducing or minimizing the diffusion. This depends on the application. But in many of the cases, as I mentioned, since there is heating in the material, definitely there is a diffusion that is going to take place, and we have to consider it when we are investigating what are the new properties that this material is going to attain up on the heat treatment. We have to consider also the diffusion mechanism into account. So that's why in this chapter we are discussing diffusion. And remember, the objective of this course is to study how the changes or things that happening at the atomic scale or the material microstructure, how they can be reflected over the material properties. This is the objective of this course. Diffusion is one of the mechanisms, one of the things that is happening at the atomic scale by migrating the atom from one lattice site to another lattice site due to heat. So it is important to understand what is a diffusion is. Make sense? All right, so what are the requirements of atom diffusion or atomic or atom migration or diffusion motion? What makes an atom leaves its lattice site that represent its static equilibrium to another lattice site? So the atom diffusion requires there must be an empty adjacent site. It means that, for example, this atom is going to move from one lattice site to another lattice site. So there should be an empty lattice site for this atom to move into, right? Another condition is that the atom must have sufficient amount of energy to break the bond. So this is one reason, one importance why we need energy. This energy is going to be used to break the bond. This is one thing with its neighbor atoms. Another thing, then it causes some lattice distortion due to the displacement or the migration. When these atoms, it means that we need the energy for two purposes, for two reasons. We need the energy first to break the bond because this atom at its own lattice site, it forms like bonds between the neighbor atoms, as we discussed before, right? So for this atom to migrate, it means that we have to break these bonds first. Then this atom is going to migrate to another lattice site, or is going to diffuse to another lattice site. So breaking the bond requires energy, and the easiest ways of achieving this energy is heating the material. And this is what is kind of consistent with the vacancy formation. As we discussed in chapter 4, to form vacancies, we should heat the material, right? To break these bonds. So once we break the bond, now the atom became free. We are releasing the atom, but this doesn't necessarily mean that the atom is going to move. To move the atom between the other crowdedness of these atoms, it means that this atom requires more energy to be pushed, to move, to diffuse between the atoms to attain another lattice site that should be empty, or reserve it for this atom, new atom, migrated atom. Make sense? So it means that we need the energy for two reasons, for two things. First, to break the bond, to release the atom at its own lattice site, but now the atom, it is just released. But it is not necessary for the atom to move, to migrate. To push this atom to migrate, you need another amount of energy that it should be big enough to keep pushing this atom to the new lattice site. Even the amount of energy that is needed to push the atom to migrate to the new lattice site, it could be, in many of the cases, is higher than the amount of energy needed to break the bond. So it means that if we could able to heat the material, not all heating the material could be used for diffusion. Heating the material, we could heat the material to break just the bond, but the atom won't gonna be able to move. Why? Because the amount of heat, it is not big enough to push the material to migrate to another lattice site. But if we heat further, if we heat more, increase the temperature, it means that there is a possibility for two things, for breaking the bond, plus then after that, there is a possibility for this atom to migrate or to move, to diffuse between the other atoms to the new lattice site. While this atom is migrating or moving between the lattice site, definitely is going to achieve or perform some lattice distortion while it moves between the lattice site. Assume that this is like you do have multiple rows of or planes of atoms in this way, and these atoms are at their lattice sites, and for some reason there is another atom that is migrating from one lattice site to another lattice site. So this is the migrating or the diffused atom. So for this atom to move, to diffuse, this space between these two atoms and these planes, it is not big enough to allow for the easy diffusion of this atom. So this atom, when it tries to diffuse, is going to push this atom here, this side, and this direction. This will result in a lattice distortion, as we discussed in chapter 4, the imperfections in crystals. And it's going to keep moving. So there is a lattice distortion that is going to instantaneous, at this instant of time, is going to take place at these two atoms. Then after a while, this atom it will attain this position. So it's gonna push this one and push this one, and it's going to achieve another instantaneous lattice distortion between these two planes or these two atoms. The same thing after a while it will be here. So there is another lattice distortion. So as it moves, it's gonna keep pushing to have way, its own path or way to the new lattice side while it migrates. All of this requires energy. It is not done by luck. No, it requires a certain amount of energy to achieve this diffusion. So diffusion in general requires energy, and in many of the cases it requires heating the material, as we discussed. Mechanisms of diffusion, it could be vacancy diffusion or interstitial diffusion. So we'd have two approaches. Remember that we'd have two types of diffusions. We'd have interdiffusion, which impurity diffusion, which happening between two different materials. Atoms are exchanging lattice side between two different materials, or self-diffusion, atoms exchanging side between the same material type. These are the types of diffusions, but the mechanisms of diffusions are a different thing. So these are the types of diffusions, but these are the mechanisms of a diffusion. What does it mean, a mechanism of a diffusion? It means how the diffusion is going to take place, how the diffusion is happening, right? This is what does it mean, a mechanism of a diffusion. So we have two mechanisms, vacancy diffusion and interstitial diffusions. What does it mean, vacancy diffusion? It is an easy thing. That is, the atom leaves its normal lattice site to attain a position to an adjacent vacant lattice site or vacancy. Like, since there is vacancy there, as we discussed in chapter 4, we said that it is kind of impossible to find that this pure material that is 100% full of atoms. Definitely there should be some vacancies. So the vacancies, it is like a default thing, is a default kind of defect inside the material structure. So as shown here, for example, there is an empty lattice site. If we try to heat the material, this atom is going to migrate. It's going to leave its lattice site and to attain this new vacant lattice site that is empty already. So there is no exchange here. There is no exchange. So the amount of energy needed, it would be lower than the exchange process, because to exchange two atoms, it means that there is one atom here and there is another atom here. This atom is bonded. This atom has its own bonds with the neighbor atoms. So for these two atoms to exchange sites, we should apply an amount of energy. This energy first is going to break the bonds of this atom, and we need another amount of energy that needed also to break the bonds for the other atoms. So we are increasing the energy in this case. Then we need one amount of energy to move this atom to the new lattice site, and we need another energy. So 4 types. The total energy to achieve this exchange, we can break it down into 4 parts. One amount of energy, an amount of energy needed to break the bonds of this atom. Another amount of energy that is needed to break the bonds of the second atom, and an amount of energy needed to migrate or move or diffuse this atom to the new lattice site, and the 4th amount of energy needed to migrate the second atom to the other lattice site. This is if we decided to exchange. One atom is going to exchange its lattice site with another atom. But here there is no any other atom. It is only one atom that has some bonds with the neighbor atoms. So we need one amount of energy to break the bond, and then another amount of energy just to diffuse this atom to the new vacant atom lattice site. Make sense? So we just need 2 parts of the energy. It means that almost half of the energy, we don't need them for the case of the vacant diffusion. So the vacancy diffusion, the atom leaves a normal lattice site to an adjacent vacant lattice site or vacancy. This mechanism, it could take place in self-diffusion or interdiffusion. We said that the interdiffusion, it means that it could be happening between 2 different materials. Like for example, these atoms, blue atoms could represent the host material, and this green atom, it could represent the impurity material for the case of interdiffusion. Or even it could be the same atom of the same material type in case that we are talking about the self-diffusion. This indicates that the vacancy diffusion can take place in both self-diffusion and interdiffusion. Make sense? But in interstitial diffusion, the atom migrates from an interstitial position to a neighbor one that is empty already. Interstitial, it means that, and this is likely to happen in interdiffusion only. Why interdiffusion only? It cannot be, there is no possibility for this in self-diffusion. In interdiffusion, here we are talking about interstitial diffusion. Interstitial, it means that there should be an impurity atom. This atom, it should be of a different material type, that it should be inserted in between the vacant or the gaps between these different atoms. So this is the atom site. This is a normal lattice site or atom site. This is another normal atom site, another normal atom site, and so on. This is the host material, and we do have, this is the impurity material as we discussed in chapter 4. This impurity atom has been inserted by interstitial diffusion into this gap between these different normal atom sites. So it has been inserted here, and upon heating further the material, this atom, it could leave its interstitial position into another gap, into another interstitial position, it's gonna fit into this gap, for example, or this gap here, or this gap here. So it is kind of interstitial diffusion. There is no stealth, there is no atomic exchange, there is no atomic exchange in this case, but instead we do have an impurity atom that is going to change its gaps that it attain within the lattice structure of the host material. So the atom migrates from an interstitial position, this is an interstitial position, this is the gap between the normal lattice sites, to another neighbor one that is empty already to fill into. This is known as the interstitial diffusion. This mechanism occurs in interdiffusion of impurities that have atoms that are small enough to fit into the interstitial positions between these different normal lattice sites or atom sites. Make sense? So these are the 2 different mechanisms that we would have for the vacancy diffusion or the interstitial diffusion. How about the exchange? Exchange, it is kind of doubling the vacancy diffusion, because to exchange, it means that you should move, as we explained, it should move one atom to fill into a vacant, and this vacant, it could be originally filled with another atom. So this atom also should do the same mechanism. It means like you should have one atom that is going to do vacancy diffusion in this direction, and there should be another atom that is going to do a vacancy diffusion but in the opposite direction. So this is gonna be kind of exchange. So exchanging, it means that you require double the energy that is needed for the vacancy diffusion. So the vacancy diffusion can represent the diffusion of one atom to an empty lattice site only. Also, it can represent the exchange, but exchange, it means that you need double the vacancy diffusion. You need one atom that do the vacancy diffusion in this direction, and the other atom do the vacancy diffusion in the opposite direction, so we can exchange in that case. Make sense? So these are the different mechanisms and different types. So we do have 2 types of diffusion: interdiffusion, self-diffusion, and we do have 2 mechanisms: vacancy diffusion and interstitial diffusion. Alright, so now we have discussed what is a diffusion, what are the different types of diffusions, what are the mechanisms of diffusion. Now let us discuss how we can measure or identify the rate of the diffusion. What does it mean, the rate of the diffusion? We can understand it simply the speed of diffusion. How fast this diffusion process is going to happen. how fast these atoms are going to migrate from one lattice site to another lattice site. So this is simply the rate of diffusion. So it requires a measure. Measure, it means that something that evaluate the rate of this diffusion, and simply we can understand this diffusion by the change of the concentration, because it would be hard for us to physically see how these atoms are moving. Assume that if we would like to record a video of the migration of these atoms from one lattice site to another lattice site, this is not that easy. This requires very high technology that would require recording this movement of the atoms from one lattice site to another lattice site. So if we do have this recording, we can measure the rate, kind of physically measure the rate of the migration of these atoms, and which could be considered as a measure of the diffusion. But it is not that easy, as I mentioned. But simply we can understand the diffusion as the change of the concentration of one material substance inside the material structure. And we discussed the composition of the concentration in chapter 4, like in case that we do have an alloy that is made of two elements, we can simply calculate the concentration of one element with respect to the concentration of the other element within this alloy. And we represented these concentrations, whatever, based on the weight of these atoms, the atomic weight of the material, or the atoms of this material, or based on the number of atoms that could be found in form this alloy. So it means that again that we can change or expect, if there is a change in the concentration, if there is a change in the concentration of one material at another position, at a certain position, this indicates definitely there is a diffusion that is going to take place, especially in case that we have two different materials. Like for example, like the case here, for this pure copper and pure nickel. Before diffusion, the concentration of nickel within this half. So for example, I have brought this thing. So this is before diffusion, this is after diffusion. So before diffusion, we do have this part. It is 100% copper. There is 0% of nickel atoms. Here we do have this side. It is full of nickel atoms, and there is no any copper atoms. So if we decided to represent the concentration of the nickel and copper, how would it change over the x, where x represents this position. So let us assume that this is the x coordinate. Like here we do have, this is the 0, and this is the positive x, this is the negative x side. Assume that. Okay, so to represent this, if we're gonna consider that this is the, let me use different color. So if this is like the x-axis that we have, and if we decided to represent the concentration of the nickel, so the nickel, it will be over this region from this is the start point and this is the end point of the nickel side. So it will be entirely 100% of nickel, and then it suddenly drops into 0 over the other side, right? So it will be 0 here, there, over this side it will be 100% of nickel. But on the other side, the copper, it will be different. The copper over this side, it will be 100% copper, right? And then it suddenly drops into 0, and it will be 0 over the other side. So these two figures, or this representation, represent the distribution of the concentration of nickel atom and copper atoms over this position. So this is the position, this is the x coordinate. Like for example, if we choose at this position, what is the concentration of the copper and the nickel? At this position, the copper, it is 100%, and I'm sorry, the nickel, it is 100%, but the copper, it is 0%. Over this position, the copper, it is 100%, but the nickel, it is 0%. Make sense? But if we allow the diffusion to take place, what's going to happen? That there should be an exchange. This copper atom is going to leave its lattice site to attain another lattice site over the other side. The same thing for the nickel atom is going to migrate or diffuse to the other side. So there is kind of exchange in the atom, and diffusion is going to take place. This definitely it will result in a change in this figure. What is this figure? This is the concentration distribution over the x-axis. This is the concentration change over position. So this will result. So if we choose the same position that we choose here, at this position here, what will be the concentration of the nickel and the copper? They won't gonna be 100 and 0. We gonna end up with other concentration for both of them. This indicates that there is a diffusion that have been happening. So the diffusion can be understood or can be measured by the rate of a change in the concentration of the two substances, the concentration of the two material in the nickel and the copper. If there is a change in the concentration, this indicates that there is a diffusion that have been happened. If there is no change in the concentration, this also indicates that there is a high possibility that there is no diffusion that have been happened. Make sense? So the change, we can simply, understanding this, we can simply measure the rate of the diffusion or measure the diffusion by the change as a change in the concentration. Alright, so another aspect that should be considered is that the change in the concentration upon diffusion, it is time dependent in many of the cases. So what does it mean? It means that, for example, if we assume that you already giving the permission of these atoms to exchange sites. So initially, the concentration distribution will take this figure, then after 1 second, it will be changing to approach this figure. Like you're gonna have 100% of the nickel, then it suddenly will be decreasing. And remember that this is the 0. Here we're gonna have a sudden decrease from 100 directly to 0, but here we're gonna have a transition between the 100 to the 0% concentration. So we're gonna have like a smooth transition from the high concentration to the low concentration. So this is the distribution, the concentration distribution for the nickel and the copper after, let's say, like 3 seconds or 1 minute or 2 minutes or 1 hour or 2 hours. It depends on the material time. So after a certain time, the distribution or this figure is gonna take a certain shape. And after more time, this distribution is going to change. It means that the concentration of these two elements is going to change continuously over time. This is what is normally happening in any material. So diffusion, and as we mentioned, the diffusion, it can be measured as a rate of a change or as a change in the concentration. So since the concentration is going to change over the time for the nickel and copper as long as there is a diffusion that is going to take place, so the concentration is going to change. This indicates that diffusion is generally time dependent. Also the diffusion, it is a time dependent diffusion. It depends on time. It means that the rate of the diffusion is going to change over time because the concentration is going to change over time. Thus, the concentration of one material varies over time and position. It varies as a function of x and t. What is x? This is the position, which is x. And t stands for the time. So what does it mean? This means the concentration, for example, of copper, it should be a function of x and time. Forget about the time. It is a function of x as we understood. At x equals 0, the copper it is 100%. And it is going to keep like 100%, then it's going to decrease. So at this position, the copper concentration, it changes. So that's why it should be a function or varying over x. Here it will be keep on changing to attain 0 when x equals a certain value. The same thing for the nickel. It is 100% over this side and is going to decrease as it approaches 0 till it at x exactly equals 0 is going to attain 0, for example. This is at certain instant of time. So this indicates that the concentration of the nickel and copper, they are position dependent. They depend on x. They are functions of x. In the meanwhile, as we discussed, this figure, is going to change with time. After a while, we're going to end up with another figure. We're going to end up with another distribution. For example, after 2 hours more, we could have the nickel is going to change or varies to in this form. So we're going to end up with another figure for the nickel. The same thing for the copper. It could change into, after a while, into this form. So we're going to end up with another figure after a while, it means that also the concentration, it should be a function of time. So generally speaking, the concentration of any one of these two substances, it varies over the position, also it varies over the time. So if we consider the time, this indicates that the diffusion, it is time dependent. The diffusion is going to change over time as well. This is generally speaking. But in some cases, after a while, after a very long time, a very enough time, this concentration would be time independent. It means that we could, after a while, we're gonna end up with a distribution, with a concentration distribution for copper and nickel, and these distributions will not change over time. This reaches us to a state is known as steady state diffusion. So we're gonna reach a steady state diffusion. What is the steady state diffusion? This is the instant or the state or the case at which the concentration of the two elements will not change over the time. It means that the diffusion, it will not change over the time. In this case, the diffusion is a steady state. So what is a steady state diffusion is? Steady state diffusion, simply, this is the diffusion that is independent of time, that does not depend on the time. In this diffusion state, the concentration of the elements will not change over time. It will be constant, but it will be only a function of x. It means that in this steady state thing, the concentration will be only a function of x. There is no time dependence in that case. Make sense? So to understand the steady state diffusion further, let us consider the example of a heating material. Why heating? Why heating the material? Because this is the mechanism or the way by which we can achieve diffusion. We said that diffusion requires energy, and there is this way of achieving this energy is heating the material. So if we just focus on the heating process of the material and how this process, it is very similar to the diffusion of the material. So assume that this candle represents like the source of the heat. And this is a material sample, and this has a length of L. This L stands for the length, and this is the X coordinate, which should be 0, and this X is going to increase to be maximum at L. So because of the heat source that we are applying to this material, at every point, at every position, there should be another temperature. It means that there is a temperature at this point that could be different or the same, like the next point, the same thing here, the temperature could be different and so on. So how we can determine the temperature at every point? We can simply attach or connect this, attach a thermocouple to that point, so this thermocouple is going to determine the temperature, how it would change over time at any point. So if we attach a thermocouple at the end, at this point, this is like a thermocouple. Okay, at the end of this material sample, this thermocouple is going to give us like a reading. It's going to keep reading the temperature, how it would change. So if we try to graph or to draw the change of the temperature of this point only, forget about the other point, just this point over time. So this is the temperature of at X when it is equal to L over time. So this is the time. So initially this temperature, it will be like a certain temperature before heating. So assume that this is like the room temperature. Like assume that we brought this material at the room temperature, then we are going to heat this material. So initially the temperature, it will be of this point, it will be the room temperature, then it's going to increase with time, right? It's gonna keep on increasing with a certain rate till at a certain instant of time, which it should be big enough, this temperature, it will be like almost constant. It's gonna keep constant, and it will not be time dependent. So before that, on the left of this line, so there is like a transition time. At this time, instant of time, on the left of it, the temperature of this point, it is time dependent. It do depend on time. And on the right of that point, or this instant of time, this like T critical, for example, or T steady state, we're gonna end up with that this temperature, it will be time independent. So this is on the right, it will be steady state. This is known as the steady state condition of heating this material. and this is known as the transient state of heating the material. Transient state, it means that on the left, at any instant of time lower than this TSS, which stands for SS stands for steady state, it means that the change in the temperature of this point will be time dependent, or the temperature of that point, it will be time dependent. This indicates that beyond this instant of time, the diffusion also is time dependent, because the diffusion, it is dependent on the temperature. The temperature at this point is going to change. It's going to keep on changing over time. This indicates that the diffusion is going to change. Why the diffusion is going to change? Because the heat is the thing that produces or enhancing the diffusion. As we heat more, we are providing more energy, so we are enhancing the diffusion, we are increasing the rate of the diffusion. So before this temperature, this time instant of time, the diffusion will be time dependent, it will be transient diffusion, and beyond this this instant of time, it will be steady state diffusion. Why? Because the temperature will not depend anymore on the time. This indicates that the concentration will not be dependent on time. This also indicates that the diffusion will not be independent on time. So here the focus is over the steady state diffusion. We can study the transient diffusion within this instant time, but it is more complicated and require more advanced models of analytical to investigate how this concentration is going to change over time. And this basically covered in a course known as the transport phenomena, or the transport of mass or ions or atoms from one side to another side, and how would it change over time. This required the study of the transient diffusion. But the study of the steady state diffusion, we assume that we give enough time to the material to heat the material, and at the instant that these points over the material, their temperature will not change over time, we are going to study the diffusion. This is known as a steady state diffusion. So the steady state diffusion, it means that we are studying the diffusion within this period of time, not this one. Make sense? This requires transient diffusion. Okay? Alright, so how we can measure this steady state diffusion, we can use the diffusion flux, which is J. J, this is known as the diffusion flux. It is the rate of mass diffusion. It is the rate of mass diffusion. It is the speed. It measures the speed by which the mass is going to diffuse. General. We said that diffusion is a general concept that we can apply to any subject. If we decided to apply the diffusion to material science, so the mass that is going to transfer or diffuse is or migrate is the atoms. So the rate of the atomic mass diffusion, this is known as the diffusion flux. So it is the rate of the mass diffusion, which is the mass diffusing through and perpendicular to a cross-sectional area of a solid part per unit time. So that's why this is the definition. This is the mathematical expression of the diffusion. It is the mass that is going to be diffused through and perpendicular to a cross-sectional area of a solid part. Like, for example, assume that you have a solid material, and let us choose like one line. This is like a plane. So this plane, it has a certain cross-sectional area, right, of this material, and assume that you do have an atom, and this atom, it should be migrated from this side to the other side, from this lattice side to another lattice side over the other side. So it means that it's going to move through this plane, and it's going to move in a direction that is perpendicular to this plane. So it means that this area, it should be identified in a direction that is perpendicular to the direction of the diffusion. So what does it mean this? It means that diffusion, it has a certain direction. Like this atom is going to diffuse along x-axis only. So it's going to diffuse horizontally. So we're going to choose a plane that is perpendicular to this diffusion direction. This is the cross-sectional area, which is A, time t. We're going to measure how long this will take for this atom to move or migrate from one lattice side to another lattice side. This is the time t, and this m stands for the mass of this atom. This is going to give us the diffusion rate, or the rate of the mass diffusion, which is known as the diffusion flux. How about if we decided to move two atoms? We're going to do this, or three atoms. So the mass is going to increase. So instead of having only the mass of one atom, we're going to end up with the mass of 3 atoms. And we're going to measure the time for these 3 atoms to move from this side to this side. We're going to measure the time, how long it takes. Also, we're going to calculate the cross-sectional area, that is through which these atoms are migrating from this side to this side. We're going to end up with the diffusion flux. So this is the general expression or definition. What is a diffusion flux? It is a kind of measure that identifies the rate or the speed of achieving the diffusion inside the metal material. Make sense? We can also represent this J in terms of the concentration. As we discussed here, we said that the concentration, it is kind of related, it is kind of way that identifying whatever there is a diffusion or not. If there is a change in the concentration, this definitely indicates that there is a diffusion that is going to happen. So the diffusion in the steady state, the concentration will be only function of X. As we said, in the steady state diffusion, the concentration will be only function of X. It will not be function of time. So it is only function of X. There is no time dependency here. So simply we can determine also J as negative D. D, it is a constant or a coefficient, is known as the diffusion coefficient, which is measured as meter squared per second. So it is meter squared, stands for area per unit time. dC by dx, this dx is known as the change or the slope of the concentration change, or the rate of concentration change over position, where x, this is the position, so this is the derivative of the concentration function, which it should be function of x. So if you already given the concentration as a function of x, you're going to find the derivative of this function, plug it here, you're going to end up with the diffusion flux. This law or this expression is known as Fick's first law. I'm pretty sure that the chemical engineer did have an idea about this Fick's law before, especially if you studied any course related to the transport phenomenon. Make sense? But anyway, this is the way how we can represent this diffusion in terms of the change in the concentration over position. This is going to give us the diffusion flux. So this is the general expression, and this is the diffusion flux in terms of the concentration. D, again, this is the diffusion coefficient. C, this stands for the concentration, which it should be measured as kilogram per meter cube, which is like a density. So this is like the material density at this position. How will it change? How would this one is going to change over the position from one position to the other one? This gives the concentration. This negative sign here, note that the negative sign in this expression indicates that the direction of the diffusion is down the rate, the concentration gradient from a high to a low concentration. So this dx over dc over dx is known as a gradient. This is like the rate. Like for example, if we said that the rate of a change in position, this gives the velocity or the speed of an object, right? So the change over position, this is known as gradient. So this is the gradient of the concentration, which is very similar to the slope of this concentration function, or similar kind of to the rate of a change of this concentration. But instead of using rate of a change, we're gonna use the gradient of this concentration. Anyway, this negative sign indicates that the direction of the diffusion, it is opposite to the concentration gradient. Like for example, if we're gonna go back here to this figure, as you can see, the rate here, the nickel, this is the direction of the diffusion of the nickel, right? So the rate of, in this direction, the nickel, it should be decreasing. So that's why we have the negative sign, because the slope, for example, if I ask you, how about the slope of this nickel from mathematics? The slope, because this represents like a straight line, and this line is going to have a slope. So the slope of this nickel, it will be dc of the nickel by dx. This is the gradient of the concentration that is already shown in the equation and the Fick's law there. This positive slope indicates that to increase the diffusion rate, to increase the J, because we define, for example, let us define the J as D times the dC by dx only. Forget about the negative. If we remove the negative, this indicates that this J, which is the diffusion flux, which represents the diffusion rate, is going to increase as long as the nickel atoms moving right or diffusing right in the right direction. Because why? Because this slope is positive, and to increase, to have a positive slope, it means that it should be moving or diffusing in the right direction. It's moving this way, right? But this is not the case. The diffusion, actually, it should be on the opposite direction. So that's why we are putting or plugging this negative. Why? Because if we remove the negative, as I said, this positive, this slope here, it is positive. This positive slope indicates that the diffusion, it should be in the right direction, in the positive x direction, because this function is going to give us x, and j, it will be depending on the positive x direction, which is not true. Why? Because the nickel, it should be diffusing left to end up with a decrease in the concentration, right? From the right to the left side, indicating that the diffusion, it should be on the opposite side. So that's why this negative, it has been plugged there. Make sense? So this negative indicates, this negative sign, it is an expression that indicates that the direction of the diffusion, it is opposite or down the concentration gradient from high concentration to a low concentration. Make sense? So let us consider this example here on the calculation of the, or applying the Fick's law, first law for the diffusion flux calculation for a plate of iron. So the plate, it is mainly made of iron, is exposed to carbon. This is known as carburizing process. Like we are adding carbon to the iron. We said that adding the carbon to the iron, this is going to end up with an alloy, and this alloy, it will be the steel. It means that we are making steel. Like assume that you have a plate of iron, and we are going to expose this plate of iron into carbon-rich atmosphere on one side of the plate. Like this is the plate, and we're gonna have very, like initially we're gonna have like 1% over this side. We're gonna have 1% of carbon. This is the iron Fe, and over this side there is no carbon. And this carbon will be diffused. What does it mean, diffused? It means that the carbon atoms will be over this surface, and it will start to diffuse in this direction. So this is the direction of diffusion. It means that this carbon atom will start to migrate from the high concentration to the low concentration. So this is the high concentration side, and this is the low concentration side. So according to what we define from as diffusion, it means that the carbon atoms will start to migrate or move from this direction, transport from this side to the other side. Make sense? Depending on what? Depending on the amount of heat or temperature at which we are going to heat this plate. So we have to heat the plate. There is very high concentration of carbon over this side and very low concentration of carbon over the other side. Once we heat the material, this plate, these carbon atoms will start to diffuse. So a plate of iron that is exposed to carbon-rich atmosphere on one side, and a carbon deficient atmosphere, which is known as, like you can understand, as low concentration of the carbon over the other side at a temperature of 700 degrees Celsius, which is 1300 degrees Fahrenheit. This is the temperature of this plate. If a condition of a steady state is achieved, it means that it takes time. Steady state, not the initial thing that is going to take place. No, initially we start with transient diffusion, and after a while we're gonna end up with a steady state. So assume that we reach already the steady state condition. We achieve the steady state condition. We waited enough time for the steady state to take place. So assume that if the condition of the steady state is achieved, calculate the diffusion flux. What is the diffusion flux? This is J, how much it is, of carbon through the plate, of the concentration of the carbon at two different positions were given as 5 millimeter and 10 millimeter were given by these two values. So as I said, this is like the position one, which we're gonna give it symbol like position A, and this is position B. XA, XB stands for the two positions. At position A, which was at 5 millimeter of the material and from this surface, and this was at 10 millimeter from that surface. So these are the two different positions. The concentrations were given by 5 times 10 to the power negative 3 and 10 to the negative 2 meter over, or which are equivalent. I'm sorry, these are the positions in terms of meter, not millimeter. Beneath the carbonizing surface are 1.2 and 0.8 kilogram meter cube. It means that the concentration at A and the concentration at B were given by these two values. At A it was like 1.2, but at B it was 0. kilograms per meter cube, which stands for like the density at this position. These are the concentration at these two different positions of the iron plate. Assume that the diffusion coefficient was given. What is the diffusion coefficient? This is uppercase D. At this temperature was given by this value. How much is D? So according to the Fick's first law, D it should equal to the negative D times dC by dx, right? It means that we should have the concentration D, which is the diffusion that is already given to us by 3 times 10 to the power negative 11 meters squared per second. So there is no problem with D, but how about the gradient of C? The derivative of C, this requires that you should have the C function as a function of X. How the concentration of the carbon over this iron plate is going to change over X, over the position. It means that we should have the concentration as a function of X. But if we can refer to this figure here, this one, we said that the concentration is going to be like, for example, if we choose, this is like FC, this is like the Fe, and this is like the carbon. So initially the carbon over one side, it will be like 100%, then it's going to decrease linearly. Almost it is like a linear function, then it's going to attain a 0. So if we assume this is like kind of a linear function, like a straight line, this is like the how this concentration is going to change over the position within the alloying region. We said that this is like a pure copper, this is like a pure nickel. In between, we're gonna end up with copper nickel alloy. So within the alloying region, the change in the concentration of one element and the other element, both they gonna represent like straight lines, like linear functions. So if we assume this, we can simply determine this gradient of the concentration as the difference in the concentration divided by the difference in the positions at two different positions. Like we can simply define this concentration at the concentration of point A negative the concentration at point B divided by the position at point A negative the position at point B. Or B over A, it depends. So this is gonna give us the concentration, how it's going to be changed. Make sense? This is we can approximate the gradient of the concentration over X by this value as long as we do have like a linear, because this is gonna represent the slope of, because this dC by dx we mentioned this is the slope of this linear relation. So we can determine this slope as the difference as CA negative CB divided by XA negative XB. So this term, simply this is what represents the gradient of the concentration, assuming that we do have like a linear change of the concentration over the position X. So if we plug this data here, we already have D equal 3 times 10 to the power negative 11. It is already given to us equal times the concentration at A was given by 1.2, negative the concentration at B, which is already given by 0.8, divided by the position. These positions were 5 millimeter and 10 millimeter. We converted them into meters. Why? Like 5 times 10 to the power negative 3 meter and 10 to the power negative 2 meter. Why we are converting to meter? Because the diffusion was given in meter square. The concentration was given as kilogram per meter cube. So we have to achieve consistency in the units. So this, it means that we have to convert into meter. So if we did the calculation, we're gonna end up with the diffusion by this value. As you can see, the diffusion is positive. It means that the diffusion, this flux, it is positive. It means that the direction of the diffusion of the carbon, it moves to the positive X direction. Why it is positive here? But for example, for some reason, if we made the concentration over the other side, it means that instead of having the high reach concentration carbon over the left and the low concentration carbon on the right, how about if we swap? If we make the high concentration over the right and the low concentration over the left, it means that the diffusion should be negative, in the negative X direction. So in that case, we have to swap the values. It means that the CA will be 0.8 and the CB will be the 1.2, for example. So this is gonna give us a negative on the top here. If we divide it, you're gonna end up negative times this value, I'm sorry, this is gonna give us here a negative, and there will be a negative in the denominator because this denominator is gonna give a negative value in that case. So the negative will be cancelled with the negative. We're gonna end up here with a negative J. So J will be negative, indicating that the direction of the diffusion will be in the negative X in case that we swap the high concentration and low concentration sites. Make sense? So it means that that's why this negative, it is important to plug it here to indicate the correct direction of the diffusion of these atoms from one side to the other side. Make sense? Alright, so last thing here as mentioned, he mentioned like assume a diffusion coefficient equal of this value at this temperature. So what does it mean this? This indicates that the diffusion coefficient itself, it is not a constant for this material. It is a material dependent, yes, for sure, but also in the meanwhile, it do depend on the temperature. So it is temperature dependent. It means that according to this statement, that the diffusion coefficient equal to this value at this temperature. So this indicates that at any other temperature, probably this this coefficient would be with a different value, right? So the question is how we can determine or calculate the diffusion coefficient D that depend on the temperature. D, which is the coefficient, the diffusion coefficient equal D0. This D0, this is like the diffusion coefficient, which is like a constant that is independent of temperature. So it is a temperature independent pre-exponent, or like this is an equivalent diffusion coefficient that is independent of the temperature, which will be counted as a material constant independent of the temperature, times the exponential of the negative QD divided by RT. QD, this stands for the activation energy of diffusion, which is very similar to the activation energy of vacancies that we covered in chapter 4. I'm just going to write the expression for the vacancies. The number of vacancies, it is N times the exponential of negative QV divided by KT. If you remember, if you recall this expression from chapter 4. So this is how we can calculate the number of the vacancies that is going to generate upon heating the material at a certain temperature. This requires QV and activation energy that would activate the vacancy formation. We said that to form a vacant atom, it means that we should achieve or have an amount of energy. This amount of energy needed to break the bonds between these atoms. This amount of energy is known as the activation energy for the vacancy. So that's why we added the subscript V, stands for the vacancy activation energy. But here the activation energy for diffusion, we are using QD, which is similar to this QV but different. Why different? Because the diffusion, it is a different mechanism that is different than the formation of a vacancy mechanism. In diffusion, we have to break the atoms. In addition, we have to achieve or apply certain amount of energy to push the material to migrate from one lattice size to another lattice size. So the activation energy for the diffusion, in many of the cases, it is higher than the activation energy for the vacancy formation. Make sense? So D, it is D0 exponential of negative QD divided by RT. QD, this is the activation energy of diffusion, which could be given in joules per mole or electron volt per atom. In case that it was given in joule per mole, so in that case, the R, this stands for the gas constant, will be 8.31. In case that this was given in joule per mole as joule per mole Kelvin, or it could be 8.62 times 10 to the power negative EV per atom, which is electron volt per atom Kelvin. In case that the temperature was, definitely the temperature should be in Kelvin in both. But this is in case that the activation, you're going to use this constant with this value in case that the activation energy was given in electron voltage per atom. In case that it was given in joules per mole, you're going to use 8.31. Make sense? Then the temperature, it will be the absolute temperature or the temperature at which we are calculating this diffusion. As we said, this diffusion coefficient, it is temperature dependent. So at this temperature, how much is this diffusion? This temperature should be in Kelvin. Alright, so let us consider this example of the calculation of the diffusion coefficient at certain temperature. It is required to compute or calculate the diffusion coefficient for magnesium and aluminum. So this is the diffusion of of one material substance, which is magnesium, which will be diffused through the aluminum alloy or pure metal at 550 and 50 degrees Celsius. So this is the temperature that is already given. So as we define the expression D equals D0, it means that this D0, this diffusion, it should be given depending on what? Depending on the two materials, depending on the magnesium that is going to migrate through this environment, which is the aluminum itself. So this D0, it will be given to us, this is the D0. Yes, it is already given here. There is some tables that we can define this diffusion data, like D0 meter square per second for the iron, how much it is for the carbon, but it depends on, it is like couple of material, like iron in a host of another iron material. But this iron, it could be BCC or iron as gamma iron, which is FCC. We said that the iron, it has like two different crystal structure. We have iron with BCC crystal structure and another iron with FCC crystal structure. Also, so the diffusion of the iron atom in the same, and the host material will be also high iron, but with BCC crystal structure, so D0 will be 2.8 times 10 to the power negative 4, and it will be 5 times to the 10 power negative 5 in case that we do have another crystal structure, which is FCC. Carbon in iron, alpha iron, which is BCC iron, it will be 6.2 times 10 to the power negative 7, but it will be different for the same also carbon diffusion in. So this is the diffusion. This side, any one of these atoms, this is the atom that is going to move. And this is the host metal, that this is the environment in which this atom is moving. So carbon in iron will be 2.3 times 10 to the power negative 5. Copper in copper, it will be 7 point and so on. So zinc in copper will be a different value and so on. So it means that this diffusion constant, which is D0, which is independent of the temperature, it do depend on the two materials, which material migrating in which host material, right? In this case, we do have magnesium that is migrating in aluminum. So the magnesium, which is Mg, migrating in aluminum. So this is the diffusion value. This is the D0 value that we needed here. It is 1.2 times 10 to the power negative 4. So D0, we got it from the table 1.2 times 10 to the power negative 4, which is already should be in meter square per second. Make sense? So we got the D0. How about the QD? This is the activation energy. The activation energy also, it do depend on the two materials. So the activation energy, for example, for magnesium, in aluminum, it will be in 1.131 kilojoules per mole, or it will be 1.35 electron volt per atom. It depends on the unit system. So they are two equivalent values, but two different units. Make sense? So it depends on which unit that you prefer to use. So let us use the kilojoule per mole. So we're gonna get the activation energy from this table next to it. It will be 131 kilojoules per mole. We have to convert it into joules per mole, so it will be 131,000 joules per mole. Make sense? So this is the activation energy, and this is the diffusion constant that we got from this table. Now let us do the calculation. So simply you're just gonna plug into this data, and the temperature is already given to us by 50 degrees Celsius. We have to convert it into Kelvin by adding 273 to this 550. We're gonna end up with the temperature in Kelvin. Since we are working using the activation energy in joules per mole, we're gonna use the gas constant. It will be 8.31, so it will be 8.31. And the activation energy, we already got it from the table by 131,000 joules per mole. And don't forget the negative exponential D0 that we got by 1.2 times 10 to the power negative 4. Do the calculations, you're gonna end up with the diffusion, how much it is exactly as we are increasing the temperature. Make sense? So it will be decreasing. In that case, it will be 5.8 times 10 to the power negative 13 meter square per second. It means that the diffusion rate is going to decrease as we mentioned. Alright, so that's it for chapter 5. We won't gonna cover any more in this chapter. Again, the objective here was to discuss the diffusion. The key condition is just to understand what does it mean diffusion, and to practice how we can do some simple calculation about the diffusion flux, especially for the steady state diffusion. All right, so that's it for today. Thank you so much for watching, and see you in the next video.